This is the first video in our atomic structure and nuclear decay unit. Our first video is on basic atomic structure. As you can see from the list of learning targets and the first standard, our essential standard here is being able to apply knowledge and understanding of the composition and structure of atoms. In this first video, we will actually look at all 5 of these learning targets. And there is a 6th that we will hit on the next video about atomic mass. But just jumping right in here, we want to be able to identify and describe subatomic particles. So what we want to understand is that atoms are everywhere. Our entire universe is composed of atoms. One way to think about an atom is that it is the smallest particle of any element. Note, elements would be the entire periodic table. So every one of those elements is composed of atoms. The atoms of every element are different. In other words, hydrogen atoms are different from helium atoms, which are different from lithium, etc. What we're going to look at here in this video is really how these atoms are different. So the structure of an atom. Atoms are composed of 3 subatomic particles: protons, neutrons, and electrons. Here is a basic schematic of an atom, and what we know about atoms is that the nucleus, which is the center of the atom, is composed of those protons and neutrons, and electrons are outside of the nucleus. Now this particular schematic or picture is like many other pictures of atoms in the fact that it represents electrons as orbiting the nucleus, kind of like our Earth orbits the Sun. Now we know now that electrons don't actually do that, but it is still a useful model for thinking about atoms. So some things about protons. We know that protons are positively charged, or they're represented with a 1+ charge. Their mass is approximately 1 atomic mass unit, or AMU for short. Neutrons are neutral, thus they have the name neutrons. They have a neutral charge, or no charge. Their mass is also about 1 atomic mass unit. Finally, we have electrons. Electrons are negatively charged. Electrons have a mass of much less than 1 atomic mass unit. So nearly all the mass of an atom comes from the protons and the neutrons. Here are some review questions. As each question pops up, please pause the video and answer the question. Which elements are made of atoms? All elements are composed of atoms. What are the 3 subatomic particles that compose atoms? The subatomic particles are the proton, the neutron, and the electron. Question number 3. Where is the nucleus in the atom? Which particle or particles is in it? The nucleus is found at the center of an atom. The nucleus is composed of protons and neutrons. Where is the majority of an atom's mass located? Explain. Nearly all of an atom's mass is located in the nucleus. This is because the particles in the nucleus, the protons and the neutrons, are much heavier than electrons, which are not in the nucleus. Does the nucleus have an overall charge? The answer here is yes. The nucleus of any atom is positively charged due to the presence of positively charged protons. So we've taken a look at that first learning target, being able to identify and describe subatomic particles. The next thing we'll do is we'll look at defining some terms here: atomic number, mass number, isotope, and along with that, using some proper chemical notation for describing atomic structure. So one thing we want to understand is that every atom of different elements are different. So the question is, how is an atom of one element different from an atom of another element? Well, atoms of different elements have a different number of protons. This leads us to our definition of atomic number. The atomic number of any atom or any element is simply the number of protons in the nucleus of an atom. So if we look at 2 elements, in this case we'll look at nitrogen and oxygen. If you look at any periodic table, you will see the atomic numbers of elements on that table. For nitrogen, you'll notice the atomic number is 7. It is often listed at the top or towards the top in the middle, and for oxygen it's 8. So what this tells us is that all nitrogen atoms have 7 protons, and all oxygen atoms have 8 protons. There is no such thing as a nitrogen atom with 6 protons or 8 or 12, it doesn't matter. Likewise, there is no such thing as an oxygen atom with anything other than 8. So again, some review questions. Question 1. What determines the identity of an element? The atomic number, and thus the number of protons, defines an element's identity. In other words, all you need to know is how many protons the atom has, and you will know what element it is. Question 2. How many protons are in a magnesium atom? Looking at your periodic table, find magnesium, you'll see its atomic number is 12, and thus any magnesium atom has 12 protons. Question 3. There are no copper atoms with 31 protons. Explain why this is. Well, if you look at your periodic table, you'll see that the atomic number of copper is 29. Thus, all copper atoms contain 29 protons. The atomic number defines what the element is. If an atom has 31 protons, it would be a gallium atom because the atomic number of gallium is 31. Are atoms of the same element identical? I want you to consider 2 carbon atoms here. Must they be identical? Well, they both must contain 6 protons because they're carbon. The atomic number is 6, so they have to have 6 protons. Assuming they're both neutral, they would both have 6 electrons because you have to have the same number of electrons as protons for the charges to cancel. So what about the neutrons? Must those be identical? Do the carbon atoms have to have the same number of neutrons? The answer is actually no. They don't have to be identical. They could be, and in many cases they will be, but they don't have to be. This leads us to the definition of an isotope. Isotopes are atoms of the same element with different numbers of neutrons. So here are 3 pictures of 3 different carbon nuclei, nuclei being plural for nucleus. Each of them has 6 protons because they're each carbon, so they have to have 6 protons. So notice here that these red dots indicate the number of protons. You can see there are 6 of them in each nucleus, so each of them is carbon. The blue dots represent neutrons. You notice in this first one here, that has 6 neutrons. The second one has 7. The third one has 8. And we can see that the nuclei are different. Thus, the atoms are not identical. They're all carbon atoms, these are all 6 protons, but they're not identical atoms. So using this idea here, these same carbon atoms as an example, let's take a look at what we call mass numbers. Isotopes, they're differentiated by mass numbers. The mass number of any atom is simply the number of protons plus the number of neutrons. Note, this mass number is not on the periodic table. You can't look at a periodic table and find the mass number for an atom because the mass number only applies to one particular isotope. One weird thing about a mass number, it's not actually a mass. In other words, if I look over here at these examples, for carbon 12, and notice it's called carbon 12 because there are 6 protons and 6 neutrons, the mass of that atom is going to be about 12 AMUs. And actually, this is kind of a bad example because the mass of carbon 12 is exactly 12 AMUs because of the way the atomic mass unit is defined. The better example here would be carbon 13 and 14. So for carbon 13, its mass number is 13 because 6 protons plus 7 neutrons is 13. And we learned in a previous slide that the mass of a proton and a neutron are about 1 atomic mass units. So when you add those together, 6 plus 7 is obviously 13. The mass of this atom would be roughly 13 atomic mass units. It's not exactly 13 though. Likewise, carbon 14 would be about 14 AMUs. It's not exactly 14. So what is the mass number of each atom here? Okay, let's take a look at a nitrogen atom with 8 neutrons. Well, I know nitrogen has 7 protons because it's atomic number 7. I add the 8 neutrons to it. That gives us a mass number of 15. There are 2 ways that we could write that and talk about that particular isotope. One of them is to use the entire name of the element, just write out nitrogen, put a dash, and then put the number 15. And we would just read that as nitrogen 15. We could also use the symbol for the element, which is capital N, and then the mass number goes as a superscript on the left side. We would read both of these the exact same way. So if you saw either of these in text, you would just read them as nitrogen 15. What about an atom with 24 protons and 30 neutrons? Well, 24 protons plus 30 neutrons is 54, and that would be chromium 54 because chromium is atomic number 24 if you look at your periodic table. So we either just write it with the whole name, chromium-54, or we'd use the symbol, and again, both of these we would simply read as chromium 54. What about a sodium atom with 13 neutrons? So look at your periodic table, find sodium. It's on the left side. You'll see that it is atomic number 11. So 11 protons plus 13 neutrons makes for 24 total. So again, we'd write it either with the name of the element, sodium, and then dashed in the mass number, which we would just read as sodium 24. Same thing if we use the symbol and the superscript there with the mass number 24 in that place. Let's consider two isotopes of chlorine, chlorine-35 and chlorine-37. So here's a picture of what we might see on the periodic table for chlorine. Which atom has more protons, the chlorine-35 or the chlorine-37? Well, it's neither of them because they're both chlorine atoms, so they both have 17 protons. That's the atomic number of chlorine. Every chlorine atom will have 17 protons. Which has more electrons? Again, neither. Assuming both atoms are neutral, they will both contain 17 electrons because those 17 electrons have to cancel the charge of the 17 protons. Which atom has more neutrons? Well, that would be chlorine-37. It's going to have 2 more neutrons than chlorine-35 because its mass number is 2 greater. 37 is 2 more than 35. So the chlorine-37 would actually have 20 neutrons because 17 plus 20 is 37, whereas chlorine-35 would only have 18 neutrons. How many neutrons does each isotope contain? Well, actually, I just answered that. Chlorine-37 would have 20 neutrons because the 37 mass number minus the 17 protons would be 20 neutrons. Likewise, for chlorine-35, it would have 18 neutrons because 35 minus 17 is 18. So here are some review questions. Please pause the video, answer the questions, and then play the video, see if you got them right. All right, true or false? Atoms of the same element must be identical. Explain. This answer is false. Atoms of the same element do not have to be identical. While atoms of the same element must contain the same number of protons, they may contain different numbers of neutrons. Question 2. What is the term for atoms of the same element with different numbers of neutrons? Atoms of the same element with different numbers of neutrons are called isotopes. Question 3. What is a mass number? Mass number of an atom is the number of protons plus the number of neutrons in the nucleus. Question 4. Write the symbol for an iron atom with 30 neutrons. While looking at the periodic table, you'll see that iron has 26 protons, so 26 protons plus the 30 neutrons gives you a mass number of 56. So the symbol we would write, the symbol for iron is Fe, and then the mass number goes as a superscript there on the left side. And again, we would just read that as iron 56. How many protons and neutrons would be in an atom of aluminum 27? Looking at the periodic table, you will see that aluminum is atomic number 13, so it would have 13 protons. And then in order to have a mass number of 27, that would mean 14 neutrons, because 13 plus 14 is 27. Alright, so we've looked at the terms atomic number, mass number, and isotope. We've used proper chemical notation for describing that structure. Now we're going to look at simply determining the number of subatomic particles in any given isotope. This is really just a review of what we've done so far in this video. So putting it all together, we're just going to fill in this chart. We're going to assume all atoms are neutral. So the chart is very simple. We just have columns for isotope, atomic number, mass number, protons, neutrons, and electrons. And we'll do a few here as an example together, and then you'll do a few on your own. So the first one here, we're given the isotope lithium-7. So looking at your periodic table, find lithium. I know half the battle here is just finding the elements as you become familiar with the periodic table and where everything is. So if you find lithium there, it's towards the left side. You'll see it's atomic number 3. So ask yourself, what does that tell us about a lithium atom? Well, if it's atomic number 3, it has to have 3 protons. And since we're told to assume all atoms are neutral, it also has 3 electrons. Now the mass number, again, that is not on the periodic table. If you look at lithium and you see that 6.94 there, that is not a mass number. It's actually something called an atomic mass. That will be covered in the next video. The mass number is just given to us here. It's 7. Recall, that's what this notation tells us. For this particular atom, this mass number is 7. So because the mass number we know is 7, we can now find the number of neutrons. We know that the protons plus the neutrons must equal the mass number. So that obviously gives us 4 neutrons then, because 3 protons plus 4 neutrons gives us a mass number of 7. Okay, next one. This time we're given the mass number and the number of electrons. Well, based on this, if I have 9 electrons, that means I have to have 9 protons. And if I have 9 protons, the atomic number must also be 9. And then for my neutrons, I know that the mass number is 19, so the protons of 9 plus whatever the neutrons are have to add up to 19, so the neutrons has to be 10. Now as far as figuring out what the isotope is, just look at your periodic table, find atomic number 9, and you'll see that is fluorine. So this is fluorine 19. Okay, again 19 because that's the mass number that we actually we were given here, but it is the protons plus the neutrons. Alright, last one here we'll do together. We're given 25 protons and 29 neutrons. So based on this, we know that there have to be 25 electrons to cancel with the protons. We also know the atomic number must be 25 because it has to be equal to the number of protons. The mass number we know is the sum of the protons and the neutrons, so 25 plus 29 gives 54. And if you look at your periodic table for atomic number 25, you'll see that that is manganese, not to be confused with magnesium, but this would be manganese 54 because that is our mass number for this particular isotope. Okay, here are 3 more. Just try on your own. Pause the video. Go ahead and fill out your notes there. Fill in the missing blanks and then play the video, see if you got them right. Alright, first one here, this time we're given the symbol. Now note, this is not any different than the information we're given up here, except we just have to look at the symbol and figure out what that element is. So looking at your periodic table, you'll see that that is gold, 197, and the atomic number of gold is 79. Thus there are 79 protons, and because it's neutral, 79 electrons. We're given the mass number of 197. Again, that is what that notation tells us. That's the mass number for this particular isotope. And then to determine the number of neutrons, that will just be the difference between the mass number and the protons. So subtracting 79 from 197, you will get 118. Alright, the next one here, we're given atomic number and neutrons. So the atomic number 36 tells us there are 36 protons and 36 electrons. The mass number is the sum of the protons and neutrons, so adding those together, you'll get 77. And looking at your periodic table, atomic number 36 is krypton, so krypton 77. And you could either write it with the symbol, or you could write out the whole name of the element, either one. And then finally, we're given a mass number of 109 and 47 protons. So if we're given 47 protons, that means we have 47 electrons, so it's neutral. It also means the atomic number is 47. To find the number of neutrons, we will simply subtract the protons from the mass number. That will give us 62. And then looking at our periodic table for atomic number 47, we'll see that is in fact silver, Ag, and the mass number here is 109. So silver, 109, as you see written there. Okay, some review questions here. Again, pause the video after each one, answer it, and then play the video. Determine if each statement is true or false. Explain your answer. Well, statement 1. Nitrogen 14 has the same number of protons as nitrogen 15. This is true because the atomic number of nitrogen is 7. All nitrogen atoms have to contain 7 protons. We know if we have 2 elements of 2 atoms of the same element, they have to be the same number of protons. Question 2. Nitrogen 14 has the same number of neutrons as nitrogen 15. This is false. The 2 isotopes of nitrogen must contain different numbers of neutrons. In fact, nitrogen 14 would contain 7 neutrons, while nitrogen 15 contains 8 neutrons. Question 3. Nitrogen 14 has the same number of electrons as nitrogen 15. This statement is true. Assuming both atoms are neutral, they will contain 7 electrons, since nitrogen atoms contain 7 protons. So looking at our learning targets here, we have determined the number of subatomic particles in a given isotope. And the last learning target we'll cover on this video is this next one here, determine the number of valence electrons in an atom. This last learning target on this standard we will cover in the next video. So valence electrons. So here is another way to represent an atom where we have our nucleus in the middle. And I know you don't see any particles there, but the nucleus is represented by that red dot there in the middle. And then we have the electrons that exist in, we can think of as being in different rings orbiting the nucleus. We know that's not actually the case. And as we get farther from the nucleus, those electrons have more energy. Thus, you can see here it says increasing energy of orbits. And the blue dots here represent electrons. In other words, what we're saying here is that electrons exist on different energy levels. And valence electrons specifically are the electrons in the outermost energy level of an atom. So this particular schematic here, this atom would have 4 valence electrons. I see 1, 2, 3, 4 electrons at its outermost energy level. Again, I can't emphasize it enough. This sort of drawing, this sort of schematic, drawing electrons in an orbit around the nucleus is very useful for our thinking. It's not actually how they exist in atoms, though. So while we talk about energy levels and we talk about valence electrons, while we might picture this in our minds over here, we do want to understand that that's not actually how they exist in atoms. That's something we'll cover later in the class as far as how they actually exist in atoms, and we'll actually learn that there is no particular path or shape that they take in atoms. So what we want to understand about valence electrons is that elements in the same group on the periodic table have the same number of valence electrons. So in other words, if I just have a picture of a periodic table here, if I pick any group, now groups run vertically up and down, and notice across the top here we have group numbers. So for example, group 2 would be beryllium, magnesium, calcium, strontium, barium, and radium, and group 13 would be boron, aluminum, gallium, etc. That we see there. So if I have any elements that are in the same group, then they all have the same number of valence electrons. And based on which group it is, we can determine how many valence electrons that is. There's a very clear, simple pattern that will tell us that. Group 1 elements, so here I'm talking about hydrogen, lithium, sodium, potassium, etc., they have 1 valence electron. Pretty easy to remember. Group 2 elements have 2 valence electrons, so beryllium, magnesium, calcium, etc., have 2 valence electrons. Now at this point, the pattern skips over to group 13. Group 13 elements don't have 13 valence electrons, they have 3 valence electrons. So boron, aluminum, gallium, etc. all have 3 valence electrons. Likewise, group 14 have 4 valence electrons. This pattern continues all the way up through group 18. So group 15 would have 5 valence electrons, group 16 would have 6, group 17 would have 7, finally group 18 would have 8 valence electrons. So if you're taking notes here, if you wanted to fill that in, 15, 16, 17, they have 5, 6, and 7 valence electrons respectively. Now you might be wondering about what about these groups here in the middle that I skipped, groups 3 through 12. Well, the pattern that we identified here of 1 through 8 doesn't hold there, but what we can say about groups 3 through 12 is all of these elements have either 1 or 2 valence electrons. Now it's not important at this point that we know which elements have 1, which elements have 2. Much of our learning and discussion at this point about atomic structure, we will exclude these transition elements as they're called here in the middle. Most of our discussion will be about groups 1 and 2 and 13 through 18 as we get a basic idea of atomic structure. Alright, this concludes this video here. A lot of learning targets, a lot of information. In the next video we will look at how we describe, define, and calculate that term called atomic mass.